One of the specific cases of finding the value of C where it particularly comes in useful is in physics type problems. And so the last bit on this basics of antiderivatives, I want to approach a physics problem. Now, we recall that if you're given the position function, stands for stasis in Latin. So if we're given a position function, velocity is the rate of change or derivative of position. Acceleration is the rate of change of velocity or the derivative of velocity, which turns out to be the second derivative of position. Now what we're going to do is this. Suppose we're given an acceleration function. Since we know how to reverse the process, if we're given the acceleration function, then we should be able to find the velocity function. Since acceleration is the derivative of velocity, that means velocity should be the antiderivative of acceleration. Again, this is done with respect to t. And since velocity is the derivative of position, that means position should be the antiderivative of velocity. Now, you may express this as a much more complex, the integral of this integral. That becomes very complicated and kind of messy to write, and so we're going to forego that. But this is the basic. If you have acceleration, integral of that, the antiderivative gives us velocity, integral of that, antiderivative gives us position. So, in our problem, suppose we're given the acceleration is negative 9.6. That's the value on Earth, that's the surface of the Earth approximately. And suppose we're given velocity at time 0 is 4 meters per second. This is sometimes called the initial velocity. Anything that happens at time t equals 0 is the initial. This is an initial condition. The textbook might not give this, or you might not be given this specifically. This is the same thing as saying initial velocity is 4. Remember that velocity can be negative. Velocity is a vector. Velocity can be negative, which means it aims in the downward direction typically. So, this is the given information, and what we're asked to do is to find the velocity function. All right? Well, we know velocity is the antiderivative of acceleration. So, we know the velocity is the antiderivative of acceleration. Oh, I'm going to, these are in meters per second squared and meters per second. Very often in the middle of the problem, I will suppress the units, and then we'll just write the units at the end of the problem when we're finished. So, what is this? This is the antiderivative. Acceleration is negative 9.6. But we know the antiderivative of a constant. The integral of a constant is you reattach the variable. Which variable do we reattach? That's where the variable indicator comes in. The variable here is time. So this is negative 9.6 t plus the constant of integration. Our task is not to find this. Our task is to find the entire function. So what this means is we need to find the value for c. And that's where this specific condition, or in this case it's an initial condition, is going to come into play. So I'm going to run a lot of space here, so I'll write this a little concisely here. We know v of 0 is equal to 4. So that implies if you plug 0 in for this t, negative 9.6 times 0 plus don't know yet, that's equal to 4. Let me write that a little bit better. But this falls out, so this immediately gives us c is equal to 4. That's why given the initial conditions, given the value t equals 0 is particularly straightforward because all these values fall out. So we're given c is equal to 4. Remember, we are not done because we have not found what we've been asked to find. Make sure to state your final result. So we know that v of t evaluates at negative 9.6 t plus the constant. Plus the constant of integration, which in this case was 4.